You ever stop and think about how a search engine does what it does? I mean, you type something in, and in less than a second, it sorts through the entire internet to find what you need. It feels like straight-up magic, right? Well, it's not magic. It's one of the most incredible feats of software engineering out there. So today, let's pull back the curtain and really dig into the architecture of the web crawler, the tireless little bot that basically makes the modern internet work.
First, to get a handle on the problem, you have to appreciate the scale we're talking about. There are over 1.8 billion websites. And just to be clear, that's not pages, that's websites. The number of individual pages, oh, that's in the trillions, and it's growing every single second. It is a truly mind-boggling digital universe.
So that brings us to the big question, right? How does any system even begin to make sense of all this beautiful chaos? How does it find new pages, keep track of all the changes, and build a map of this territory that's expanding all the time? Well, the answer lies with a special kind of internet bot.
Its mission, should it choose to accept it, is to index the web. And the hero of our story, the explorer charting this digital frontier, is the web crawler.
Okay, so what is a web crawler, or a spider, as it's sometimes called? You can think of it as an automated script. Its only job is to visit web pages, read them, and then follow all the links on those pages to discover new ones. It's pretty much exactly what you do when you browse from site to site, except it does it on a massive, superhuman scale.
At its heart, the process is actually deceptively simple. The crawler starts with a starter list of web addresses. We call them seed URLs. It goes out, fetches those pages, reads through the code to pull out all the hyperlinks it can find, and then it adds all those new links to a giant to-do list called the crawl frontier. Then, it just does it again, and again, and again, endlessly. It's a simple loop that, when you scale it up, builds the map of the entire internet.
But, and this is a huge but, that simple little loop immediately slams into its first massive problem: the sheer unfathomable scale of the web.
Seriously, think about it. If just one computer tried to do this, visiting trillions of pages one after the other, it would take centuries, maybe even millennia. By the time it was done, the internet it started crawling would be completely, totally different. That approach is a non-starter. It just doesn't work.
So what do? You build an army. The solution is what we call a distributed system. Instead of one lonely computer, you have thousands, maybe hundreds of thousands of machines all working together, all sharing the load. They act as one single giant cohesive crawler that's capable of exploring millions of pages all at the same time.
All right, so we've got our army of crawlers. But managing this army brings up our second major challenge: speed. Even with all those computers, the whole process can grind to a halt because of some really fundamental bottlenecks.
So we have to ask ourselves, what's really holding them back? You'd think it's about raw computing power, but it turns out it's more about what the crawler is spending most of its time doing, or not doing.
A huge chunk of the problem is what we call I/O-bound tasks. The I/O stands for input-output. This is literally any time the crawler is just waiting. Waiting for a web server on the other side of the world to respond. Waiting for a DNS lookup to find out where that server is. All this waiting can take precious seconds, and when you're doing it millions and millions of times, it adds up to a colossal waste of time.
The other big bottleneck is CPU-bound tasks. Now, this is the actual thinking part of the job. This is when the crawler has finally downloaded the web page, and its processor has to kick into high gear to parse all the HTML, find the links, and extract the content. This is pure, heavy-lifting, computational work.
The solution to all that waiting is a fundamental shift in how you think. The old-school, synchronous way is like waiting in a line at the bank. You make a request, and then you just stand there, doing nothing until you get a response. The asynchronous way is a total game changer. You send off a request, but while you're waiting for that response, you go and start dozens, maybe thousands of other requests. You don't wait, you keep working, and just handle the results as they roll in.
So, we end up with this really elegant two-part solution for speed. For that I/O-bound waiting game, we use asynchronous operations to juggle thousands of connections at once. And for the CPU-bound number crunching, we use parallel processing to split the work across all the different processor cores on a machine. It's not just about working faster, it's about working smarter.
But, as you can probably guess, having a massive, lightning-fast crawler creates a whole new set of problems. How do you manage all that power? And that brings us to our next big challenge: staying organized and, believe it or not, being polite.
The key to staying organized is something called the URL frontier. The best way to think of it is as the air traffic controller for the entire operation. It's a really sophisticated system that manages that giant to-do list of URLs, deciding which pages are most important to visit next and assigning them out to crawler machines that are free.
And just as important as being fast is being polite. A web crawler could easily crash a small website's server if it just hammers it with too many requests too quickly. So any well-behaved crawler follows a politeness protocol. It always checks a site's robots.txt file for any special rules, it respects any requested delays, it limits how many times it hits one server at a time, and it clearly identifies itself so webmasters know who's visiting. It's about being a good citizen of the internet. Now, trying to coordinate thousands of machines and trillions of URLs brings up some really fascinating computer science problems. And one of the most elegant solutions that engineers came up with for these big distributed systems is something called consistent hashing.
Now, to really appreciate how cool this is, you gotta understand the problem it solves. Let's say you're assigning URLs to different crawler machines. The simple way to do it is with a formula like hashmod n, where n is your number of servers. But here's the problem. If you add a new server or one of them fails, the value of n changes, and nearly every single URL has to get reassigned to a new machine. It's total chaos. Consistent hashing is the stable, robust alternative.
Here's the basic idea. Just picture a circle, like a clock. You take your servers and you place them at different points on this ring. Then you take your data, in this case a URL, and you place it on the ring too. So how do you decide which server gets which URL? Simple. You just find the URL spot on the ring and travel clockwise until you hit the very first server. That's its owner.
And here is where the magic happens. If you add a new server to the ring, it just calmly takes over a small slice of work from its neighbor. If a server fails and disappears, its workload is simply passed on to the next server in line. The vast majority of the system doesn't even notice. It provides incredible stability with minimal disruption. It's brilliant.
And to make the system even more fair and balanced, engineers use a trick called virtual nodes. Instead of putting a real server on the ring just once, they give it multiple virtual spots all around the circle. This smooths everything out, prevents one server from getting a huge chunk of the work by chance, and it means that if one machine goes down, its load gets spread evenly across many other machines, not just dumped on one poor neighbor. This quote from some researchers really sums it all up, you know? Building a web-scale crawler isn't just about writing a simple script. It is a monumental challenge in system design, network efficiency, and just plain robust engineering. It's a beautiful symphony of different solutions, all working together in harmony.
And that, of course, brings us to the future. The web we have today isn't just static HTML pages anymore. It's packed with dynamic JavaScript apps, AI-generated content, all these walled-off platforms. The big question for the next generation of engineers is this: what new kind of architecture will crawlers need to not just read the web, but to actually understand it? Definitely something to think about.